Okay, so chapter 2 is all about sets. 2.1 was about sets, 2.2 is about sets, and I mean, it's just all about the different things that we're going to be able to do with sets. And so today we're going to learn some set operations. We're going to learn how to intersect our sets. We're going to learn how to union our sets. We're going to learn how to do a difference of sets. Now, intersection of sets and union of sets, you've actually seen if you took Math 20. There was a section on it in Math 20 as well. So hopefully this is just going to be a little bit of review then if you've already had that. If you haven't, that's okay. I think intersection of sets and unions of sets are pretty logical in how they come across because we can use them in the real world. So the intersection of sets is where we have two different sets, A and B. And then the intersection symbol is this little upside down U or hill. So A intersect B is the set of elements that are common or contained in both A and B. I love Venn diagrams for intersections and unions because I think it's very nice visual representation of that information. This circle on the left is our set A, and this circle on the right is our set B. So the intersection of those are the things that are in both A and B. So it's this shaded region here in the middle. And if you like our set notation, it says A intersect B is the set of X such that X is an element of A and X is an element of B. Intersect goes with and. They've got to be in both. So we see this, I think, very visually on street intersections. We even call them intersections. And if you think about 7th and Range Line, just down the road a little ways, that's the intersection of 7th Street and Range Line. You can be on Range Line and be on 20th Street or 32nd Street or towards there, but the only place that you can be on both Range Line and 7th Street at the exact same time is in that intersection right there. Otherwise, you're either on Range Line or you're on 7th Street. So to live in the intersection, you live in both. So when we are actually looking at different sets of numbers and things like that, what we're going to look for is what do they have in common? What numbers are in both of the sets that we are trying to intersect with? So we're going to do 3 examples. The first example is actually written here in my pencil as well as here in the pen. But I want to leave that definition up for a moment, and I want to leave the Venn diagrams up as well. There, now we can see all 3 of our examples. So the first set that we have is 3, 4, 5, 6, 7. We are going to intersect that with set 4, 6, 8, and 10. So what I'm looking for in the intersection is what do they have in common? Well, this set has 4, and this one has 4. This one has 6, and this one has 6. But that's it. This one has 8 and 10. The first set does not. This one has 3, 5, and 7, but this one does not. So the intersection of these two is just 4 and 6. They don't share anything else in common, and that's okay. Those are the only things. If we made Venn diagrams, those would be the 2 numbers that live in the middle section because they lie both in both sets. What about for B? B, we have 9, 14, 25, and 30 in our first set, and we are going to intersect that with the set of 10, 17, 19, 38, and 52. So what lives in that middle section? What do they have in common? Nothing. Yeah, there's nothing in common between those 2 different sets of numbers. So when we are getting nothing, that's our empty set, our null set. There's nothing in common. So if we made Venn diagrams based on these 2, they would be 2 circles that sit side by side and they don't overlap anywhere because they share nothing in common. The last one is we have the set 5, 9, and 11. We're going to intersect that with the empty set. Well, what lives in the empty set? Nothing, right? There's no elements in it. That's what makes it empty. So if it's empty and we intersect that with something that's not empty, are they going to share anything? No. So when you intersect with the empty set, you're going to get the empty set. So I put those two back to back so you can see sometimes you'll have two sets that both contain elements and the intersection is still going to produce the empty set. And when you intersect with the empty set, you're going to get the empty set. Because you can't have an intersection of nothing with an intersection of something and it actually share anything. There's a special name for like B. What happened in B where we had two sets that intersected and we got nothing? That's called disjoint. So sets A and B are called disjoint if A intersect B produces the empty set. Disjoint just means they have nothing in common whatsoever. Are there any sections about intersections? I don't know if I just said that right. Are there any questions about intersections? Maybe that's what I said. I don't know if that's what I said. That's what I meant. It's still a little early. So intersection is what do they have in common? Unions are where you combine two sets. The union of sets A and B, which is written as A with this funky U, B, and both the union symbol and the intersect symbol are available on Pearson if you need to type them in anything. But the union of sets A and B is the set of all elements belonging to either A or B. So for intersection, we had the word and. You had to live in both. For union, you just have to live in one of them. So when we look at a Venn diagram, we have set A, we have set B. So the union is all of it. It's the intersection here in the middle, and it's all these other elements in A and all these other elements that are in B. Because you just have to live in one of them to live in the union. My quote-unquote real-life example for unions is a marriage. Marriages are called unions as well. But when you get married to somebody, you take all your crap and all their crap, and now it's all y'all's crap. That's how a union works with math as well. If you have a couch and you marry somebody with a couch, now y'all have two couches. So, A union B, just reading through the set notation, A union B is the set of X such that X is an element of A or X is an element of B. There's a program here on campus. I'm trying to remember. Project Stay. Some of you may or may not have heard of it. It's like the college version of Trio. It's a branch of Trio, but the college version of Upward Bound. They came and spoke to all the classes last semester if you happen to be here. But one of their things, like one of the requirements to get into there is you have to be one of a couple of different things. Like you have to be a first-time college student, or you have to like make a certain level of money, or there was one other thing, and I don't remember what it was. But like you didn't have to fulfill all of them, you just had to do one. That's how unions work. You just have to fulfill one of the sets in order to live in the union. And so unions are really quite simple in putting together. When we do union examples, what we're going to do is we're going to list all the elements from both of our sets. The only thing we kind of have to remember is we're not going to duplicate elements. So here's what I mean by that. When we are going through and writing down what these unions are, like this first one we have the set 2, 4, 6. We're going to union that with 4, 6, 8, 10, 12. I think one of the easiest ways to do unions is whatever your first set is, go ahead and just write all of those elements. Because if you live in the first set, you're going to live in the union. Plain and simple. Then go to your second set and look for new elements. Look for unique ones. We already wrote down the 4. We already wrote down the 6. We don't need to list them again. We don't have to write duplicate values. So the only things I need to add to my union are 8, 10, and 12. Now this new set represents the union of these two original sets. Every element is included. And we only have to include them once. So you don't list repeaters, you just list new ones. And this weird scribble, this is an F. I had made a oops. That's an F with our ABC one. So again, for the second one, I'm going to list everything that's in my first, and then I'm going to look for the new elements that are in my second. So in my first set, I have A, B, D, F, G, and H. So then I'm going to look. Well, I hadn't written C yet, so I'm going to write C. I did write F, G, H, so I need to add K. And if it bothers you that they're not in alphabetical order, you can list them in alphabetical order. The order of your elements does not make a difference. What about C? When we have the union of set 3, 4, 5 with the empty set, what do you think our unioned set is going to be? Yeah, 3, 4, 5. Because you have to live in one or the other. You don't have to live in both. So there's nothing that lives here. That's why it's the empty set. So really, it's like adding 0 to a number. It doesn't change anything. So it's just 3, 4, 5. Are there any questions on how unions work? You live in one or the other. You can live in both. But you're going to live in the union if you're doing the union. We're combining them. We're uniting them. Okay. I'll leave those up there. There's one additional note on this front page where it says, remember from 2.2, so that was the previous section, that A with a dash up there is called a complement. And that means everything that's in the universal set that's not in A itself. Because we're going to talk about how to do unions and intersections with our complements as well. And so that's good to remember from 2.2. These chapters very much build on themselves, and so the stuff you learn in 2.1 is important for 2.2, and that's important for 2.3, and so on. Definitely not learn it and forget it from each section. So A complement is everything that's in the universal set that's not in A. And that is from 2.2. Right, we're ready? Cool. We're going to flip over, and we're going to do some more examples. I guess I don't have to flip over. I can just slide up. I have them written here for you. We're going to do some examples using our complements. So this problem is going to apply for all 4 of our examples. They give us a universal set of 1, 2, 3, 4, 5, 6, 9. Then they specify that set A is 1, 2, 3, 4. Set B is 2, 4, 6. And set C is 1, 3, 6, 9. And then they're going to ask us for a bunch of different things that we need to find. And each of these deals with some form of complementary set. So the first one is asking us for A complement intersect B. So the first thing is up there in all of my sets, I have U, A, B, and C. I don't have an A complement. So I need to find A complement first. So A complement is the set of all the elements that live in our universe. So this U set right here, everything that lives here that does not live in A. So A has 1, 2, 3, and 4. So what else lives in U that's not there? Well, we have 1, 2, 3, 4 in A, but we don't have 5, 6, and 9. So those live in A complement. Those are the 3 elements that live in U, which is our universe, that don't live in set A. So then when I'm taking the intersection of A complement with B, what I'm doing is I'm taking set 5, 6, 9, and I'm intersecting that with B was 2, 4, 6. Oftentimes I will write the sets just like this side by side because then it helps me to see, okay, for intersection I want to look for things they have in common. Yes?
So in Pearson, for this problem, you'll include the intersect in the answer?
No, because I'm not done.
Okay.
So I will just include whatever my final set is. I'm just showing all the different steps for how we do it.
Sorry.
No, it's okay. That's a good question. So the only thing, like at the end in Pearson, it will give you the curly brackets and then you just fill in whatever the answer is. So if I'm looking at, here's A complement, here's B, what is the only things that they have in common? 6. So the intersection is just 6. Sets can be as small or as large as they need to be. So one element in a set is totally okay. So this is the final answer. Are there any questions on any of those? Okay. So for B, it says find B complement union C complement. So again, I don't have any of the complements actually given to me. I need to find them out. So that will be my first step. B complement is anything that lives in the big universe that doesn't live in B. So B has all of my even numbers, 2, 4, and 6. So that means B complement will have 1, 3, 5, and 9. Those are things that live in the universe that do not live in B. Then I do a similar process for C, because I need to find C complement. So C was 1, 3, 6, and 9. So I go through my U. They have 1, but C doesn't have 2, so C complement will. C has 3, but it doesn't have 4. And it doesn't have 5, but it does have 6 and 9. So now when I'm finding B complement union C complement, I'm taking the set 1, 3, 5, and 9 and unioning that with the set 2, 4, and 5. Remember, union means you take everything that's in the first one and you add it to everything that's in the second one. You don't list duplicates. So I'm going to simply rewrite my answer to start with my B complement because all of those will be included. And then I'm going to look for new elements in my second one, which is C complement. 2 is a new element. 4 is a new element. 5 we've already listed, so I'm not going to list it again. So 1, 3, 5, 9, 2, 4 is the resulting set. So really it was everything in the universe except for the number 6. Now some of your problems, like this next one, you're doing 2 things. You're taking A intersect B union C complement. So notice that the B union C complement is in parentheses. Just like with regular numbers, parentheses tell you what to do first. Order of operations is what's really going to happen here. Order of operations, if you remember, is please excuse my dear Aunt Sally. Parentheses happen first. So we're going to do what's inside the parentheses before we do the A intersect. Okay? So we know what B is, and actually we know what C prime is. We just did that one. We just found C prime in the problem above. So we're going to take B union C prime. Well, B from way up here is 2, 4, and 6. Whoops, that's a curly bracket. Union that with my C prime, which we just found was 2, 4, 5. So what will that equal? What is the resultant set? Exactly right. 2, 4, 5, 6. Because when you union stuff, you're just adding them together. You're combining those two sets, not writing down duplicates. So they both shared 2 and 4, but then they also had a 5 and a 6 between them. It's kind of like that movie. I don't know if there's two different versions. There's an old one and a newer one. Yours, mine, and ours. You have or the Brady Bunch. The Brady Bunch, she had 3 girls, he had 3 boys, then they joined them together. Now, they never had children together, theoretically, but it's kind of like that. They share stuff, and then they each had stuff coming into it. So now we're taking A intersect this new resultant set that we just found, which is B union the C complement. So A was 1, 2, 3, 4. We're going to intersect that with 2, 4, 5, and 6. So intersect is where we're looking for what do they have in common. Well, they don't have 1 in common. They do have 2, not 3, but they do have 4. So 2, 4 is our resulting set. So sometimes you have to do multiple things in order to actually figure out what the grand scheme is. Pay attention to where those parentheses are. Parentheses are always important in math. Okay, so the last example here is we're going to take B union C, and that's inside the parentheses, and then we are applying the complement. So you always do what's inside the parentheses first, and then after that we will figure out what the complement of that is. So B union C. We're going to take everything that was in, oh, you can't see that now. There you go. B was the set 2, 4, 6. Union that with the set 1, 3, 6, 9. Now I can scroll it up a little bit. So if we union these, we're just combining them. So I have 2, 4, 6, and then a new element would be 1, 3, 6 we already have, and then 9. That's a 1. That's a wonky 1, but it's a 1. So that's what B union C is. But now we need to find the complement of this. So we need to look at our universe, 1, 2, 3, 4, 5, 6, 9, and think about what is in our universe that does not live in this set right here. I'm going to write it in numerical order because that might help us spot what it's missing. So what is missing from here that lives in our universal set? Just the element 5. Yeah, that's the only thing missing. So that means our final set would just be the set containing the number 5. Any questions at all on this? Yes.
I'm kind of confused because on some you included like all of the numbers, and on others you just included the ones that like don't have or that has duplicates. So I'm kind of confused on when you have to do which.
So union is where you're going to list out anything that's in either of them because you're combining them together. That's the definition of union. You can live in either one.
Yeah.
Intersection is what do they have in common. And so that's when I'm looking for the duplicates.
That's what I thought.
Yeah. No, great. I'm glad you're asking questions. Because it's better to clarify it now before they get harder. So one thing to note here is that when you take the intersection, like B complement, or excuse me, I said intersection, I meant union. So when you take B complement, union, C complement, that does not guarantee that it equals the same thing as when you take the union first and then do the complement. So we have to be careful that we do not equate these. All right, let's talk about our last operator for sets. This one is new, even if you've had Math 20 before. This one will be a new one that we didn't talk about in Math 20, and it's known as the difference of sets. The difference of sets A and B looks like A minus B. So we use the subtraction symbol to mean difference. Difference is another way of talking about subtraction. So the difference of sets A and B is the set of all the elements belonging to set A and not set B. And so I noticed whenever I was looking through my notes this morning that my scanned-in notes do not have this little complement tick up here in the set notation. So just note that it should. And I will have to rescan in my notes at some point to correct that. So if you are taking the difference of two sets, excuse me, you're wanting to know what lives in A and not in B. So if we look at our Venn diagrams, we have all of set A colored in except for this intersection part. And the reason why we don't color in that intersection part is because those elements that live here would also live in B. And when we think of the difference, we don't want to think of anything that lives in B. We only want to know what elements live in A. So, reading the set notation, we have A, like the difference of A and B is the set of X such that X is an element of A and X is an element of B complement. Because B complement is going to be everything that lives in A. Another way of looking at this is thinking of we are taking A intersect B complement. That is the same thing as the difference. Oh, sorry. I'm going to zoom out a tiny bit. Nope, wrong way. There we go. So we're going to do 3 examples that involve the difference. And we have totally new sets. We have a new universe. Our universe here is 1, 2, 3, 4, 5, 6, and 7. So the numbers 1 through 7. A includes the numbers 1 through 6, B includes 2, 3, 6, and C includes 3, 5, 7. So when you're finding the difference, what you're really thinking about is whatever set is listed first, you want to know the elements that are unique to just that set. If I asked you guys, do you like burgers or pizza? Some of you would say you like pizza, some would say you like burgers. Some of you may be difficult and say, I like both. So if you like pizza, you would live in A. If you liked burgers, you'd live in B. And if you liked both, you'd live in the intersection. But if I'm going to go out for a burger tonight, or sorry, I said pizza. If I'm going out for pizza tonight, I don't really want to ask the opinions of the burger people. I want to talk to the people who like pizza. So I'm only going to concern myself with the people who said pizza. And I'm going to ask you, okay, where's the best place to get some pizza tonight? Because I don't really care what the burger people think, because they wanted burgers, and I want pizza. So that's one kind of weird way, I guess, to think of this in a real life scenario. Okay, so we're going to find the difference of A minus B. So A is first. So we want to know what are the unique elements to A that are not in B. So we're not concerned with everything that's in the entire universe. What we're doing is we're taking A. So A is 1, 2, 3, 4, 5, and 6. And we are subtracting from that the elements that live in B. 2, 3, and 6. We're literally taking out these elements from A, is what we're going to do. So if we take out the elements 2, 3, and 6, I will be left with 1. Let's see, 2 and 3 live in B, 4 and 5. This is the difference. These are the unique elements that live in only A, not in B. Notice I did not list 7 because I'm not concerned with what, like there was one person who said sushi was their favorite, and that wasn't an option. I didn't ask for your favorite food. I asked for pizza or burgers. And so that sushi person's just not included whenever I talk to people. I want to talk to numbers 1, 4, and 5 about the best place to get pizza. All right, let's look at B. I promise B is not redundant. B says, find the difference from B from A. Think about even with normal numbers. If I ask you, so this is like a little side note, you don't have to write this down, but if I asked you for 4 minus 3, you would tell me that's 1. But if I switched my numbers and I said 3 minus 4, I don't get the same answer. The order matters. The order matters in regular numerical subtraction. The order matters when we find the difference of our sets. So if I'm going to, sorry guys, I'm moving stuff kind of crazy. If I'm finding the difference of B to A, then I'm listing B first, which was 2, 3, and 6. And I'm going to take away everything that's in A, which is 1, 2, 3, 4, and 6. B was a smaller set to get started with. So when I take away everything that lives in A, what am I left with? Nothing. I'm left with the empty set. There's nothing that lives in B that isn't included in A. So there's nothing left over when I take the difference. Okay, one more. It says find, parenthesis, A minus B, then union that with C complement. Now luckily, let me talk right. Luckily, we already did this part. The A minus B was the very first thing we found. A minus B was the set 1, 4, and 5. That was part A. what we do need to figure out is we need to figure out what is C complement. Well, C complement is going to be everything that lives in the universe that is not included in set C. So 1, 2, 4, and 6 are not included in set C, but they are included in the universe. So when I union these together, remember union means I take everything from here and I combine it with everything from here. So I'm going to union those, and my final set, can you see that? Yep. I'm going to write everything here, which is 1, 4, 5, and then I'm going to look for new numbers. I already wrote number 1, number 2 is new. I already wrote number 4, number 6 is new. So my final set will be 1, 4, 5, 2, 6. So you can include differences of sets with your unions and with your intersections. Just pay attention to where the parentheses lie and which one that means you have to do first. Are there any questions at all on these? All right. So note, which we already kind of saw using basic numbers, that when you take the difference of two sets, A minus B does not equal B minus A. We saw that. When we took A minus B, we got 1, 4, and 5. When we took B minus A, we had the empty set. And so you do get different things. The order matters. So why is this important? Well, because we can talk about ordered pairs in terms of sets. An ordered pair, in the parentheses, we have our A and our B, or our X and our Y terms. The X, or the A, is our first component. That tells us our horizontal placement in a Cartesian coordinate system. The B tells us our second component, or our vertical placement in the Cartesian coordinate system. That's our Y. And so we can actually think of ordered pairs in terms of combining different sets together, where we have the set of all of our first components, and we're going to combine that with the set of all of our second components. So simply here, A, B, this ordered pair can equal CD if and only if A equals C and B equals D. The ordered pair 0, 1 can only equal the ordered pair 0, 1. That's what that means. We get these ordered pairs by doing actually a Cartesian product of sets. Again, where we're going to have a set of all of our first components and a set of all of our second components. So Cartesian product of sets A and B is where we say A cross B. That's a big X, or a big multiplication symbol. And that is the set of all ordered pairs A, B, such that A is an element of A and B is an element of B. Basically, we're going to pull the first components from our set A. We're going to pull the second components from set B. The Cartesian product of sets, that sounds pretty mathy, to be quite honest. But what we're really doing is we're grouping. We're just grouping and laying out all of the possible ordered pairs that can be arranged from using elements in A as our first component or as our X's, and then using the B elements as our Y's or our outputs. That's really all we're doing. We're kind of pairing them up. So I'm going to show you the systematic approach that I use. That way I don't forget any of my ordered pairs when I do these. So I'll leave the definition up there as we do our two examples for this. So it says, let A be the set of 1, 5, and 9. A is our first components. Those are our x coordinates. And B is the set of 6 and 7. Those are our y components. We need to find what the Cartesian product is of A cross B. So what we're going to do is we are going to pair these up so that every single one of our answers is an ordered pair within our set. So the way that I will always approach this is I'm going to look at the first element in my set A, because that's listed first, and then I'm going to write all of the possible ordered pairs that I can with that as my first term. So here's what I mean. I'm writing an ordered pair, so I have to have an x term and a y term. Well, my y terms have to come from over here, from the B column. So I'm pairing 1 with 6, and then I can pair 1 with 7. There's only 2 terms in the B set. So these are the 2 ordered pairs I can make if 1 is the first term. Then I move on and I do the same thing for 5. I can have 5 paired up with 6, or I can have 5 paired up with 7. Then I move on to my last first term. That sounds a little bit weird, but it is what it is. Where I would have 9 paired up with 6 and 9 paired up with 7. So when you are finding the Cartesian product of sets, you're going to be finding ordered pairs. And you're grouping them according to the order that they're telling you. So for this first one, A's were my X's and B's were my Y's. So my A values had to live in the X spot of my ordered pairs, where the Y values came from my B's. So let's see what happens when we flip them. Let's find B cross A. So this time our X terms are going to come from our B set, and our Y terms are going to come from our A set. But I'm going to do the same process. I'm going to say, okay, if 6 is my first term, I can pair that with a 1, or I can pair the 6 with a 5, or, that's a parenthesis, or I can pair the 6 with the 9. Then I've paired 6 with everything available to me in my A set. So I'm going to move on to 7. 7 I can pair with 1, 7 I can pair with 5, or 7 I can pair with 9. Notice for both of those, I got 6 different ordered pairs, but they're totally different ordered pairs. So the order that they're asking for the Cartesian product matters a lot. The number of ordered pairs might be the same that you're going to get out, but the specific ordered pairs that you get out are very different. So note, A cross B did not equal B cross A. We didn't get any of the same ordered pairs. We didn't get the entire set that match. Okay, let's talk about the cardinal number of the Cartesian product. This looks all scary. It's really not. If you remember back from 2.1, cardinal numbers of a set is just the number of elements that live inside the set. Okay? So if n of A equals A, so if the cardinal number of set A is this random number, and the cardinal number of set B is this random number, then we can find the cardinal number of a cross product, regardless of the order, simply by multiplying the cardinalities of the 2 original sets. Now, in math speak, I get it. That's a lot. That's a lot of math. But it actually works really, really well. And it makes a lot of sense. And we're going to use this as our example. The cardinality of our Cartesian product. What it says is let's find the cardinality of A. How many elements live in A? How many elements live in A? 3. Thank you. Be confident. 3 elements live in A. There's 1, 5, and 9. There's 3 of them. What is the cardinality of B? 2. There are 2 elements that live in B. So we have our cardinality of A, our cardinality of B. We can determine the number of elements that we will get in the cross product by multiplying these 2 cardinalities out. So if I take the cardinality of A times the cardinality of B, that'll tell me how many cross products I can get. 3 times 2 is 6. Both of our cross products had 6 ordered pairs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Cardinality is not affected by the order that we're doing a cross product. And this is a nice little cheat to make sure that we don't accidentally forget one. If I'm listing these numbers and the numbers are a little bit larger, like there's 5 elements here and there's 4 elements here, I may forget to pair one of them up and I only get 18 instead of 20. I only got 18 pairings because I accidentally forgot to pair something up. So while it won't tell you what you didn't pair up, it is a great way to go ahead and check at the end and make sure you did get all your pairings before you submit your answer. So when you're finding the cardinality or the number of possible elements that you get after you take the cross product, what you need to do is you look at the original sets that you're starting with and multiply those cardinalities together. Sounds big and mathy, looks a little bit scary written out there in all the math terms. Not too bad when you actually utilize it. That's all that says down there. Found the cardinality of A, cardinality of B. So the cardinality of A cross B or B cross A is going to be 6 because we multiplied them together. Any questions? All right, I'm going to flip over. So if you happen to have my notes written or like the scanned in ones that you're looking at, this is the next bit. This is just a really nice cohesive table that organizes everything from this section. It talks about the complements, which was actually from 2.2, the intersection, the union, the difference, and then the Cartesian product. So I just really liked how it organized it. I liked how it had all of the different Venn diagrams representing what each of these meant. I thought that was really helpful. So if you like it, feel free to print it. You can cut it out, put it in your notes. You can copy it down. But all of this stuff is really just a listing of the definitions that you've already encountered in this section or in the previous section. But it's a great reference. And there's one more thing, and it's called De Morgan's laws for sets. De Morgan's law for sets states that for any sets A and B, where A and B are subsets of the universal set, then the complement of A intersect B will always equal A complement union B complement. And if you take the complement of A union B, will always be A complement intersect B complement. And I'm going to show you this using Venn diagrams. I'm going to show you that this actually works. De Morgan was a pretty smart dude. It's kind of crazy to think sometimes when we're learning definitions or we're learning these different rules and things about math, that somebody just sat around and came up with it and proved it and showed that it worked for everything. It's pretty crazy. Might allude to why a lot of ancient mathematicians went crazy in their old age, because they sat around thinking these things up and actually were able to do it. I don't know about you, I would never come up with this. But I am going to show you how it works. using Venn diagrams. Okay. So De Morgan's law states we have two sets. They're subsets of the universe. So if we take the intersection and then find its complement, that's the same thing as if we take the complements and union them together. So what I'm going to do is I'm going to use Venn diagrams to kind of show this. So here's set A, here's set B. If I'm finding A intersect B, which is what's inside this set of parentheses, that's what lives here in the middle. So then I need to figure out, okay, so the complement of this is like the opposite. Okay? The opposite of this. So I would have these two. And if the opposite of shading the middle would be shading everything but the middle. This is A intersect B complement. Because this is everything that lives in the universe that is not included in the original intersection. So, okay, so that's like this half of this equation. So let's look at what A complement is. We have A, we have B, and I want to find A complement. A complement means you don't live in A. It's everything that doesn't live in A. Well, this whole circle on the left-hand side is A, so I would shade in everything over here. That's A complement. B complement is everything that doesn't live in B. So that's this part over here. So if I union these two things together, I'm going to union A complement with B complement. So I'm just combining these two pictures together. Notice that I have all of A shaded and all of B shaded except for that intersection parts. So this is A intersect union B intersect. Notice these two pictures in the bottom are exactly the same. I had to go through more steps theoretically on this one, but I still got the same picture. So we just showed that this is actually true. And so we could do the reverse of it, is what this states over here. So it does work. It's just kind of approaching it from two different perspectives. Am I going to expect you to memorize and state out De Morgan's law? No. But is it helpful sometimes to be able to see that these are actually equivalent whenever we're starting to work through problems and figuring out what unions and complements of different sets are? Yeah, it will be helpful.